Let's consider the strength of the lithosphere. Now, rocks are subjected to stresses in the earth, and strain is the term that describes the deformation of a rock. So you apply the stress to the rock experiences that stress, and the deformation that we see is the strain. This plot considers increasing stress on the y-axis and increasing strain on the x-axis. And let's look at how deformation in a rock changes with increasing stress and strain. When a rock is subjected to increasing stress, it passes through 3 stages of deformation in succession. The first application of stress results in an elastic deformation. These are reversible changes in the volume or the shape of the stressed rock. That's followed by a ductile deformation that is an irreversible change in the shape and or the volume of a rock that has been stressed beyond the elastic limit. And finally, the fracture happens in a solid when the limits of both the elastic and the ductile deformation are exceeded. So that's a permanent failure. The confining stress is a uniform squeezing of rock because of the weight of the overlying rock. Stress, or sigma, is equal to the density of a rock times gravity times the height of the pile of rock above it. A high confining stress hinders the formation of fractures, and so it increases the strength of rock. And a high confining stress reduces brittleness. Eventually, ductile deformation becomes the weaker mode of deformation. This plot is a result of experiments on different rock types and looking at the response to normal stress and the maximum shear stress on these rocks. This established Byerlee's law, which shows that the brittle shear strength, or tau, is equal to the coefficient of friction, mu, times the normal stress. And mu is simply the slope of this line that passes through all these different rock types. Rocks form inclined conjugate sets of brittle fractures at predictable orientations when they're subjected to compression. And you see these early wax experiments from the late 1800s that show the conjugate sets of fractures. Faults form as Coulomb shear fractures at acute angles to sigma 1, the maximum compressive stress, and obtuse angles to sigma 3, the least compressive stress, or an extensional stress. Sigma 2 is simply contained within the fracture plane. And that one of the principal stresses, sigma 1, sigma 2, or sigma 3, is vertical in the shallow earth that leads to 3 classes of faults. In normal faults, sigma 1 is vertical. In reverse faults, sigma 3 is vertical, and then in strike-slip faults, sigma 1 is roughly parallel to the fault plane. Brittle substances tend to deform by fracture, and ductile substances deform by changing their shape. And the higher the temperature, the more ductile and less brittle a solid becomes. Rocks are brittle at the Earth's surface, but at depth where temperatures are higher because of the geothermal gradient, rocks become ductile. And if we look at a stress-strain plot of rocks in the upper crust, you'll see that after elastic deformation, very little ductile deformation occurs before the rock fails and fractures. A rock in the middle to lower crust is at much higher temperatures, and after elastic strain will behave ductily or deform ductily for a much longer period before it fails. rocks will behave more ductily when they're at higher temperatures and at high confining stresses, so deeper in the earth. Those are both characteristic of the deeper crust and upper mantle. And you can increase ductility at low strain rates. And the addition of water can enhance ductile properties by weakening the chemical bonds in minerals and forming films around the mineral grains. And finally, the composition affects ductility. So quartz, garnet, and olivine are relatively brittle. So quartz is more abundant in the crust, and so in general helps the crust to behave brittly, certainly in the upper crust. Whereas mica, clay, calcite, and salt are relatively ductile. So as I just suggested, the strength of a rock is determined by its composition and the temperature and pressure that the rock is residing at. Rocks in the crust are quartz rich, and so the strength properties of quartz play an important role in the strength properties of the crust. And rock strength increases to a depth of about 15 kilometers. Above 15 kilometers, rocks are strong. They fracture and fail by brittle deformation. And below 15 kilometers, quartz weakens and rocks become increasingly ductile. And if we look at this wee plot down here in the corner, with rock strength increasing on the x-axis and the depth in the earth increasing down, you'll see that a strength profile for the crust might look like this, with an increasing strength with increasing confining pressure until the point when quartz starts to weaken at about 15 kilometers. Let's try this again. So the strength of the crust increases with depth in the upper crust, but then at around 15 kilometers, quartz weakens and the middle and lower crust behave more ductily. That happens at what we call the brittle-ductile transition, and that depth is going to change depending on the composition of the rocks. But in normal intermediate composition andesitic crust, it's about 15 kilometers. Then rocks in the mantle are olivine rich, and olivine stronger than quartz. And the brittle ductile transition of an olivine rich rock is reached only at about a depth of 40 kilometers. So in the mantle, we have olivine increasing in strength briefly with depth in the upper mantle, and then weakening below about 40 kilometers. And then by about 1300 degrees Celsius, basically the oceanosphere, rock strength is very low and brittle deformation is no longer possible. And so that's when we have the final disappearance of all brittle deformation, and that marks the lithosphere-oceanosphere boundary. Rock strength in the earth doesn't change uniformly with depth, and in the conventional jelly sandwich or Christmas tree diagram, like this one here, there are two or multiple peaks in the plot of rock strength with depth. In this one, we have the strong, crusty bread at the top of the sandwich, the weak jelly in the middle, and the strong, crusty bit of bread that is the lower part of the sandwich. And that happens to also look a little bit like a Christmas tree. Let's look at that a little bit more closely. So we have the crust, the moho, the mantle, and the lithosphere-oceanosphere boundary. The strength of the upper crust increases with depth to the brittle ductile transition that happens at about 15 kilometers. And the strength increases because of the confining pressure of the overlying rock. Then at around 15 kilometers in the corresponding temperatures at that depth, quartz weakens and starts to behave more ductily. And so the strength profile of the middle and lower crust decreases until we reach the Moho, and then we consider a different composition rock. We're looking at an olivine-rich rock in the peridotite. The strength of the olivine increases to about 40 kilometers depth, and then that too starts to behave ductilely. And so the strength of the mantle rocks decreases until you reach the limit of brittle deformation possible in the outermost shells of the earth at the lithosphere-asthenosphere boundary. And that gives us the gooey, plastically deforming asthenosphere that arises because we have a small percentage of partial melt. And so this ductile deformation gives us dramatically folded, deformed rocks like these in the Swiss Alps. And these are clastic material, nearshore material. So they must have been in the middle to lower crust to deform like this, so ductily. And what we've been discussing is really a discussion of rheology, and that is the study of how matter flows, whether it is behaving brittly or ductily. That is a difference in rheology, and that derives from the Greek word for stream or flow, and an ology, study of. Let's look at geologic strain rates. There are about pi times 10 to the 7 seconds per year. So a strain of 1 per million years is about pi times 10 to the minus 14 per second. A typical geologic strain rate, so things like isostatic uplifts, orogenic activity, and earthquake displacements, those have strain rates of 10 to the minus 12 to 10 to the minus 15 per second. An example would be a 1,000-kilometer plate straining at 10 to the minus 15 per second deforms at 1,000 times 10 to the 6 millimeters times pi times 10 to the 7 seconds per year times 10 to the minus 15 per second gives you a result of about 30 millimeters a year, and that translates to 30 kilometers a year. If we look at elastic rheology, we have to consider Young's modulus, which we'll use E to stand for. Elastic behavior corresponds to something like a spring, so the deformation is proportional to the force that you apply to it. Young's modulus is the slope of the line in a stress-strain diagram as above. In that diagram, Young's modulus is about 10 to the 10 or 10 to the 11 pascals. And at 4 kilometers depth, which corresponds to a pressure of about 1 kilobar, the strain is equivalent to the pressure divided by Young's modulus, and that works out to about 1%. If we look at creep, if we follow the imposition of a stress, we see an elastic strain. So you can see the strain versus time diagrams on the right. That is followed by 3 creep regimes. So we can see a decreasing strain rate in the first field, a constant strain rate in the middle of the upper diagram, and an increasing strain rate on the right. If the stress is removed, there's a rapid drop in strain in the lower diagram. And then we see a recovery of elastic strain followed by a period of relaxation, leaving a permanent inelastic deformation, so it doesn't return to its former state. With a viscous rheology, we have to consider viscosity, which is eta. A viscous behavior corresponds to something like a leaky dash pilot. You can think of that as a piston cylinder or that mechanism that is used to keep a door from slamming shut. The viscosity of the fluid provides a resistance to the piston. The resistance is proportional to the strain rate. So we see the stress sigma is equivalent to the viscosity times the strain rate in a Newtonian fluid. You can think of a normal fluid. Viscosity is the slope of the line in a stress-strain plot. And fluids show viscous behavior. All deformation is non-recoverable, and they deform no matter how small the strain, and strain is time-dependent. Hence, this is a concept of a geophysical fluid, and a viscous rock is rheologically a fluid on geologic timescales, but otherwise functions as a solid. For example, it transmits seismic shear waves. If we look at some typical viscosities, we see lithosphere has a viscosity that's greater than 10 to 24 Pascal seconds. The oceanosphere is slightly smaller. A rhyolitic lava is about half the viscosity of the lithosphere. A basaltic lava, less so. And then very low viscosity, 10 to the minus 3 Pascal seconds for water. So 10 bars is equivalent to about 10 megapascals, produces a strain rate of 10 to the minus 17. So that's a unit of strain in 3 billion years. Or 10 to the minus 14 for a strain rate in the oceanosphere, and that's about 100% strain in 3 million years. If we look at viscoelastic behavior, that's like a sponge filled with water. When a weight is placed on the sponge loses water. That's the viscous behavior until all the water is gone, and then the sponge supports the load elastically. An elastico-viscous behavior, a spring responds instantly to a stress, whereas the dash pot example, the piston cylinder, moves and keeps moving as long as the stress is present. When the stress is removed, the spring slowly contracts, releasing its stored energy, and the dash pot moves until the spring returns to its original state. That relaxation time is equivalent to the viscosity divided by the modulus. And that works out to about 300 years for the oceanosphere. With general linear behavior, that's a combination of elastico-viscous and a viscoelastic behavior in a series. All linear rheologies have a linear relationship between stress and strain, such that the stress is equivalent to the viscosity times the strain rate. In a nonlinear rheology, and that applies to many geologic materials, especially silicates, at high temperatures, the relationship isn't linear. The stress is proportional to the effective viscosity times the strain rate to the power of 1 over n, where n is greater than 1. And the strain rate is a function of stress. This is a stress-dependent viscosity. The elastic plastic behavior model is an example of a nonlinear behavior and is shown by a block and spring model. You can imagine pulling a block along with a spring. The strain accumulates, the block moves, and then it's in a relaxed state again. Now, the relationship between stress and strain, that constitutive equation of nonlinear rheologies, has this form. It's a strain rate is equal to an empirically derived constant A times the stress to the exponent n, where that's the stress exponent that typically has a value between 1 and 5 for most rocks, multiplied by this exponent of an activation energy E, which relates to the minimum energy necessary for creep to start in crystals. You can see those typical values. R is the gas constant, and that's expressed in units so that it's dimensionless. And T is the temperature in Kelvin. That equation can be rewritten in terms of stress, so that stress is equal to that empirically derived constant A times the strain rate, to the power 1 over n, times exponent E divided by RT. And if we substitute known values of A, N, and E at constant strain rate and temperature, that allows us to compare the relative strength of different rock types. On the left, in the first plot, we see that we're holding constant the pressure and the temperature, and there's a variable strain rate. And what that plot shows us is that rocks are weak at low strain. So we have strain percentage at the bottom on the x-axis and a differential stress on the y-axis. So low strain rates, rocks are weak. In the central diagram, we hold temperature and the strain rate constant, and we have a variable pressure. And again, we see rocks are weak at lower pressure. On the right-hand side, we hold pressure and the strain rate constant and have a variable temperature. And in this diagram, we see rocks are weak at high temperatures. This table shows a list of experimentally derived values. And if we solve for that constitutive equation using these data, we find that the differential stress on the right-hand side is much lower for salt than any other rock type, and that can explain why salt flows so easily. And if you compare different rock types, compare an olivine-rich rock that is dry to an olivine-rich rock that is wet, you'll see that wet rocks are much weaker than dry rocks. If we look at creep strength versus depth and corresponding temperature, you see that if you look at an olivine-rich rock, that it is much stronger to greater depths and higher temperatures than a quartz-rich rock would be. Let's bring back Byerlee's law. That was this equation that we looked at earlier, where the brittle shear strength is equivalent to a coefficient of friction times the normal stress. That gives us this line here where the shear strength is equivalent to 0.8 times the normal stress. And the normal stress corresponds to the pressure of the overlying pile of rocks, so depth beneath the surface. And above this line, rocks fail brittly. Beneath this line, rocks don't fail. Byerlee's law is what gives us this strength profile for oceanic lithosphere, or could be continental lithosphere, where rocks are strong with increasing depth to a point at which whatever mineral is the strongest in that crust starts to weaken at those temperatures, and then they become weaker. So in oceanic lithosphere, it's olivine dominated, so it's stronger to greater depths, but at some point around 40 kilometers, olivine does weaken. So there are some important controls on lithospheric strength. Oceanic crust is olivine dominated, so it's strong to greater depths. The mantle is also olivine dominated. But the continental crust, at least the upper crust, is dominated by quartz, and quartz is relatively weak, much weaker than olivine. The continental lower crust is comprised of plagioclase and pyroxene dominantly, and plage and pyroxene are also relatively weak compared to olivine. Temperature is controlling the depth at which these rocks deform according to Byerlee's law. So when you might have brittle failure, and how they deform ductily according to a power law creep. The lithosphere is strong above this point and weak beneath it. If we look at a strength profile for the continental crust, you'll see that the crust is strong to about the mid-crust, let's say about 20 kilometers depth. And that's where quartz starts to weaken, and we see the decrease in strength to the Moho, at which point the olivine-dominated mantle rocks are quite strong, again to a certain point, where temperatures are high enough that it weakens olivine, and those rocks weaken. That's giving us this Christmas tree diagram. And these are drawn for a particular strain rate and heat flow. And the shape and position of these curves is strongly dependent on the strain rate and on the temperature of these rocks. And of course, the composition of the crust is very important on the shape of this curve, because if, for instance, the lower crust wasn't plagioclase and pyroxene rich, but contained more mafic minerals, that would be stronger to greater depths. These lithospheric strength profiles are what gives us the jelly sandwich model for lithospheric strength, wherein we have a brittle upper crust, which is the top piece of bread. Then the middle of the jelly sandwich is this ductile lower crust, and then the next piece of bread at the bottom of the sandwich is the brittle and strong upper mantle. Now, that conventional multi-layer jelly sandwich model, wherein each new layer of a different rheology causes a new strength contrast. And so we could get a Christmas tree looking diagram like this, wherein we see the strength increase with depth to a certain point where the dominant mineralogy starts to weaken, a decrease in strength, an increase in strength again at the next layer, and so on. If we look in some more detail at this strength profile for continental crust, we would see that in tectonically stable crust, with increasing depth, the lithosphere is deforming in a brittle failure first, then stores stress elastically, and then finally deforms ductilely. On the right-hand side of this diagram, if we see an increase in stress or temperature, or simply with the passage of time, the accumulated stress in the elastic core of the crust grows because brittle failure above and ductile creep below both dissipate stress, and the elastic core shrinks. The regions of brittle and ductile failure converge, and eventually we get this whole lithosphere failure. If we consider typical geologic strain rates for different composition of crust or mantle, we see that for quartz, above 300 degrees Celsius, we will see ductile behavior. For a lower crust that's comprised of plagioclase and pyroxene, the ductile behavior starts at temperatures that are between 500 and 600 degrees Celsius. And then for an upper mantle peridotite, that ductile behavior starts at around 800 degrees Celsius. If we look at standard continental geotherms, so how temperature increases with increasing depth in the earth, these imply that for an average crust, that the middle and lower crust are ductile below about 10 to 30 kilometers depth, and that the upper mantle is ductile except in just the coldest, shallowest parts of that uppermost mantle. If we look at an accumulated stress depth diagram for a 3-layer lithosphere, so considering the upper crust, lower crust, and mantle, If we apply an extensional force over a 100-kilometer lithosphere at a constant heat flow of 60 milliwatts per meter squared, we can see what the stress depth profile would look like after 1,000 years, 10,000, 100,000, and 1,000,000 years. And what you see are just increasing differences in the rheological properties between the upper and lower crust and the mantle. If we look at a similar diagram, but this time for variable heat flows, and we're looking at lower heat flow on the left, 45 milliwatts per meter squared, up to 90 milliwatts per meter squared on the right, what you see are not only an exaggeration between the rheological properties in the three parts of that lithosphere, but you see an increasing strength in the upper crust and a decrease in strength in the lower crust with increased heat flows. Now, if we consider a critical stress level and heat flow that's required for permanent deformation in the continental lithosphere, and this is within 1,000,000 years, here this is a critical stress and heat flow. We see that this pink area represents the heat flows and the stresses that are required for permanent deformation, and this is an extensional environment. In compressional environment, it's a smaller area, which higher critical stresses and higher heat flows are required for that permanent failure. And looking at regions that are undergoing a measurable deformation, we can, for example, see the East African Rift and the Basin and Range. Those areas require heat flows of 80 to 100 milliwatts per meter squared for that kind of deformation. And that's an active extension area. We can look at also Paleozoic crust that's deforming in Central Europe or Northern China. Those regions are also have elevated heat flows of around 70 milliwatts per meter squared. But then compare that to stable shield, where heat flows range from 20 to 50 milliwatts per meter squared, so much lower heat flows. Now, again, looking at these strength profiles, if we consider an area like Cenozoic and Mesozoic rifts with elevated heat flows somewhere around 70 milliwatts per meter squared, this is warm lithosphere with measurable deformation. You'll see that we do have this weakened lower crust and a stronger upper crust. Whereas in Archean craton, and this could apply to any shield area where there's very cold, rigid lithosphere, we see this more well-established strength profile that we're used to seeing in those Christmas tree diagrams. Now, different heat flow implies different jelly sandwiches that leads to different styles of deformation. In a core complex, where heat flow is very high, here 100 milliwatts per meter squared, all of the strength in the lithosphere is in the uppermost crust. In a wider rift, perhaps like the Basin and Range, still high heat flow, but less than a core complex, we see there's still strength in the upper crust, but we also see a strong upper mantle. That's exaggerated further in a narrow rift area with more normal heat flow of around 60 milliwatts per meter squared. We see a strong upper crust, but here the upper mantle is much stronger. If we look at earthquake distributions, the number of earthquakes versus the depth of those hypocenters, they mirror these strength-depth plots. So in hot areas like the Aegean, where young crust is extending, we see few earthquakes below 15 kilometers. In cold areas, as in Africa, that is mostly stable, there we see earthquakes even below 30 kilometers depth. The Moho temperature is really important. If the Moho has a temperature of 500 degrees Celsius, that implies that most of the strength of the lithosphere resides in the upper mantle, even allowing earthquakes in the uppermost mantle. At Moho temperatures of 700 degrees, that implies the strength resides in the upper crust, and the overall strength is much lower. And this is a quote from Peter Molnar. Only fools or unusually insightful individuals not yet recognized to be ahead of their time would doubt that the warmth of the lower crust in regions of extension makes decoupling of the upper crust and upper mantle more likely there than in other settings. Thus, the real challenge to understanding how such decoupling or coupling occurs will require study of regions of intercontinental crustal shortening. Water is also very important. A dry upper mantle, the profile is here, is stronger than a dry lower crust there. But a wet upper mantle here is weaker than a wet lower crust. At the same temperature, it would be a little stronger, but because it's deeper, it's hotter. So, does the jelly sandwich model work for continental crust? There are 3 jelly sandwiches here. One is for a wet lower crust and a dry upper mantle. One is for a dry lower crust and a wet upper mantle. And one is for a wet lower crust and a wet upper mantle. They're all jelly sandwiches, but the strength in each model resides at very different depths. So with wet lower crust and upper mantle, we see that the upper crust is where the strength lies. In a dry lower crust, wet upper mantle, we see that the lower crust is where the strength resides. And then with a wet lower crust and a dry upper mantle, the strength in the lithosphere is really in the upper mantle. James Jackson will argue that the belief in a strong upper mantle comes from rare upper mantle earthquakes, but being able to better locate those foci shows that those earthquakes are actually in the lower crust. And so there's no evidence for a strong upper mantle. And his favorite example is in Tibet, where they've located earthquakes to depths of 80 to 90 kilometers in the lowermost crust. He may be wrong about Tibet. If we use better depth estimates of those foci and of the Moho depth, you can see in this seismic profile that the location of the Moho that's estimated may actually reside above some of those very deep earthquakes. But he's probably right about the principle, wherein most continental lithosphere has only a ductile upper mantle, And the most recent geotherms predict that even shields, old cold shields, have Moho temperatures in the range of 600 degrees Celsius at 55 to 60 kilometers depth. Other crust is thinner, but it's hotter. And only mantle that's less than 600 degrees Celsius can support earthquakes and behave brittly. So earthquakes at mantle depth should occur in areas of recent subduction, should only occur in areas of recent subduction, and that is where these depths are advectively cooled by that recent subduction. And one of those areas is Tibet. So James Jackson's campaign to abandon the jelly sandwich, which is probably wrong or at least overstated, he acknowledges here that earthquake focal depth distributions and effective elastic thickness variations on the continents suggest that in old cold regions such as shields, the lower continental crust can be stronger than the upper mantle, and imply that the upper mantle can flow even when the lower crust does not. However, in other places, substantial flow in the lower crust does occur, particularly near extensional metamorphic core complexes. We suggest that the lower crust only flows when its viscosity is significantly reduced, either by heating from igneous intrusions or by the addition of water. In both cases, the important characteristics of the flow are a consequence of the limited time over which the viscosity reduction occurs. This timescale is controlled either by conductive cooling of intrusions or by the separation of melt from its matrix, which removes the water. So the long-term strength of the continental lithosphere may look like a jelly sandwich, or it may look more like creme brulee, wherein the jelly sandwich that we've been discussing shows a strong upper crust, weaker lower crust, and strong upper mantle. The creme brulee model requires a strong upper crust and a weak upper mantle. There are numerical thermomechanical models that assume a free upper surface and a hydrostatic boundary condition at the lower surface. That's depicted by the springs in these models to the right. A stability test is based on a mountain range height of 3 kilometers and a width of 200 kilometers, initially in isostatic equilibrium with 0 elevation, 36-kilometer crust. They disturb the isostatic balance by applying a horizontal compression to the edges of the lithosphere at a rate of 5 millimeters per year. The displacements of both the surface topography and Moho were tracked through time. And the collision test is based on continent-continent collision initiated by subduction of dense, downgoing oceanic plate. And then assumed a normal thickness oceanic crust of 7 kilometers, a total convergence rate of 60 millimeters per year, and a serpentinized subducted oceanic crust. In the stability test, the mountain range uses the jelly sandwich and the creme brulee rheological models, where the thermal structure is equivalent to a 150 million year old plate, and the structure is shown after 10 million years. So there's been 50 kilometers of shortening. The inset, the lower figure, shows the amplitude of the mantle root instability as a function of time. The figure shows the evolution of a marker that's initially positioned at the base, so 0 kilometers, of the mechanical lithosphere. So that's the depth where the strength is equal to 10 megapascals. The solid and dashed lines show the instability for a weak, young, and old, strong plate. In the collision test, it also uses the jelly sandwich and creme brulee models. The elastic thickness, or TE, and the Moho temperature are 20 kilometers and 600 degrees Celsius for both of the models. And the figure shows a snapshot after 5 million years of structural styles that develop after 300 kilometers of shortening. The conclusions of these models that are considered by Jackson, both the strong mantle jelly sandwich model and the weak mantle creme brulee model, have an elastic thickness of 20 kilometers. That's at the high end of the seismogenic layer thickness, and the low end of the continental elastic thickness estimates. The creme brulee model that's considered by Jackson is mechanically unstable. Therefore, the weaker creme brulee models, for example, the ones with the weak upper crust and the elastic thickness less than 20 kilometers, will be even more unstable. The jelly sandwich model of Jackson is mechanically stable. Therefore, the stronger jelly sandwich models that are the ones that with a strong coupled lower crust and an elastic thickness greater than 20 kilometers will be even more stable. In the models, Burov and Watts argue that subduction and orogenesis require this strong mantle layer, that the weak mantle is mechanically unstable and tends to delaminate because it's unable to resist the forces of tectonic origin. So the creme brulee model isn't stable. Once it does delaminate, the hotter and lighter mantle oceanosphere flows up, leading to widespread partial melting and magmatic activity. And hence there is further weakening such that subduction is inhibited and surface topography collapses in a relatively short time. These models were published in 2006, and the conclusions are basically that the creme brulee model is unable to explain either the persistence of mountain ranges or the integrity of downgoing slab in a collisional system. There is almost certainly no one type of strength profile that characterizes all continental lithosphere, that the creme brulee model, any weak mantle model, may apply to some specific settings, so that might be a young hot rift such as parts of the Basin Range in the western US and northern Tibet, but that the jelly sandwich model, so any strong mantle model, is more widely applicable, so for example rifts, orogenic belts, and cratons. So the jelly sandwich wins.